A Starlink antenna has to point at a satellite flying across the sky at about 27,000 kilometers per hour. So how does it keep up? While the dish has motors for initial alignment, mechanical movement is far too slow and jerky to actually track the satellite. So instead, Starlink uses phased array beam steering. So what is a phased array? In a phased array, instead of a single large antenna, we use a grid of multiple small antenna elements.
But how can a phased array control the direction of the signal without any mechanical parts? In wireless communication, information is transmitted using electromagnetic waves, like radio waves. Every antenna radiates electromagnetic waves, much like dropping a stone in water creates ripples. These waves travel outward as expanding circles or spheres in 3 dimensions. Each wave has peaks called crests and valleys called troughs. The distance between 2 crests is the wavelength. When multiple antennas transmit simultaneously, their waves spread out and overlap. What happens when these waves meet? When 2 waves overlap, they combine through a process called interference. If the crests of both waves align, they're in phase, they add together, creating a larger wave. This is constructive interference, making the signal stronger. But if a crest meets a trough, they're out of phase, they cancel each other out. This is destructive interference, reducing or eliminating the signal.
So, how does this interference help the Starlink antenna create a laser-like focused beam? Start with a single antenna emitting radio waves in all directions. Since these waves travel at the speed of light, they take time to travel outward. Now add a second antenna. Focus on a point exactly in the middle of these 2. Since the distance from both sources is identical, the waves arrive at the exact same time. They arrive in phase, combining to form a larger, stronger wave. In fact, every point along this center line receives maximum intensity due to constructive interference. But move to a point along the side, in line with the antennas. Here, the wave from the farther antenna must travel an extra distance, a distance equal to the spacing between the 2 sources. If that spacing is exactly half a wavelength, the wave from one antenna will lag behind. One arrives as a crest, while the other arrives as a trough. They cancel each other out completely. This is destructive interference, and the signal simply disappears. If we map the signal strength for every point in space, we see a distinct pattern. The bright zones represent maximum amplitude. Since radiation intensity is proportional to the square of the amplitude, these areas are very strong. When we combine this interference map with the natural loss of signal over distance, we get the final result, the antenna radiation pattern.
So we see that radiation can combine to create entirely new properties. Start with an isotropic antenna, which radiates equally in all directions. It sends waves outward like ripples in space. Here, the dark areas represent low signal, and the lighter areas represent high signal. As you can see, the energy distributes evenly everywhere. Now, introduce a second antenna nearby. Immediately, interference creates a new complex pattern. Along the horizontal axis, the signals are out of phase, meaning crests meet troughs, so they cancel each other out completely. However, along the vertical line, the signals are in phase, crests meet crests, so the intensity doubles. Currently, these antennas are spaced half a wavelength apart. But if we widen that gap to 1.5 wavelengths, something changes. 2 grating lobes suddenly appear. This is rarely what we want, as our goal is usually a single sharp beam for precise communication. Finally, instead of just 2 antennas, let's increase the count to 4. Notice how the beam immediately becomes narrower and brighter. While we do see 2 weak side lobes appear, the trade-off is clear. By adding more antennas, you achieve a much sharper, more powerful main beam.
When we move closer to the antenna, the electromagnetic field reveals interesting patterns divided into 3 distinct regions. The area roughly 0.16 wavelengths around the antenna is the reactive near field. Beyond this, extending up to a distance of 2d squared over lambda, is the radiating near field, also known as the Fresnel region. In this equation, d represents the largest dimension of the antenna. Outside this boundary lies the far field, or Fraunhofer region. What is the significance of these regions? In the near field, the wave fronts appear very curved, making mathematical calculation complex. However, in the far field, the wave front is approximated as flat because the curvature becomes negligible. Now, let's assume we place a field strength meter in the far field. It shows the strength of the signal at that point. If we move the meter in a circular path around the antenna array and plot the readings, this plot becomes our antenna radiation pattern. But how can we find this plot mathematically? Since the measuring device is in the far field, the wavefront is assumed to be flat, meaning the radiation from each antenna travels along parallel paths. To measure the intensity of radiation at a particular angle, we simply look at the wavefront direction and sum the waves from each antenna. But here is the challenge. Each wave travels a slightly different distance compared to the others. This is called the path difference, and it means the phase of the waves will not be the same. So how do we measure this path difference to find the phase difference? Consider two antennas with a spacing of dx. The wavefront we're measuring is inclined at an angle theta from the normal line. By doing some simple trigonometry, we find that the extra distance the wave from the left antenna must travel is equal to dx times the sine of theta. Now that we can compute the extra distance, how do we get the phase difference? We have to convert this length into an angle. If we divide this length by the wavelength, we get the number of cycles the wave requires to travel this distance. If we then multiply this by 2 pi, we get the extra angle each wave needs to traverse, which is the phase difference. For mathematical convenience, we can represent these sinusoidal waves as complex exponential functions. The next step is simply to sum the values of the waves from each antenna in the wavefront direction. Now, what if we do not just have 4 antennas, but instead have a large number, n, of antennas? In this case, the phases accumulate in a regular pattern, 0, psi, 2 psi, and so on. This creates a geometric series. We're essentially summing powers of a term, r, where r is our complex exponential, e to the j psi. The formula for this sum is straightforward. It is the quantity 1 minus r to the power of n divided by 1 minus r. Through mathematical simplification, this sum resolves into the shape known as the sinc function, defined as sine theta over theta. When we plot this sinc function over different angles, we get the antenna radiation pattern, usually displayed on a logarithmic scale. However, a linear plot is not physically intuitive. If we wrap this plot around a circle, we finally get the iconic shape of the antenna radiation pattern.
Now that we understand how an antenna creates a central beam, let's look at a new scenario. Suppose our target device is located at an inclined angle, theta 0, away from the normal direction. To steer the beam to this specific angle, we must force the waves to line up constructively there, instead of at the center. From our previous steps, we know there is a physical delay caused by the extra distance the wave travels. We defined this as psi space, which is equal to 2 pi over lambda times d times the sine of theta. Currently, the phase of every wave leaving the antenna is identical. To steer the beam, we must electronically add a phase difference to each element. We will call this electronic phase beta. We apply this incrementally. Antenna 0 gets a phase of 0. Antenna 1 gets beta. Antenna 2 gets 2 beta, and so on. The total phase difference, psi, is simply the sum of the physical delay and our new electronic delay. So psi equals k times d times the sine of theta plus beta. We want our main beam to point at our desired angle theta 0. As we know, maximum constructive interference happens when the waves align perfectly, meaning the total phase difference is 0. So we set the equation to 0 at our target angle, theta 0. When we solve for beta, we get the phasing equation. It tells us if you want the beam at theta 0, you must delay each antenna by negative k times d times the sine of theta 0. Essentially, this electronic delay perfectly cancels out the physical path difference. When we plug this new definition of psi back into our standard geometric series formula, we get the final beam steering equation.
The result is powerful. Simply by electronically varying the phase, beta, we can direct the beam in any direction without moving a single mechanical part. Ideally, all energy would travel in the main beam. However, due to imperfect cancellation at off-axis angles, we see side lobes, leakage of unwanted energy. Between these lobes lie nulls, specific angles where destructive interference is total, causing the signal to drop to zero. To suppress these side lobes, we apply windowing functions, also known as amplitude tapering. Instead of driving every antenna at equal power, we keep the center strong, but gradually reduce the amplitude toward the array's edges. This smooths the radiation profile, drastically reducing side lobes. However, this introduces a fundamental trade-off. As side lobes are suppressed, the main beam widens, forcing engineers to sacrifice some directional precision to gain a cleaner, interference-free signal.
To turn this mathematics into reality, we need high-speed electronics. Let's look at the hardware architecture of a modern phased array transceiver. Since this system must both send and receive data, a component called the TR switch sits directly behind each antenna. It acts as a high-speed traffic guard, rapidly toggling to connect the antenna either to the transmission chain or the reception chain. When the system is in transmission mode, the signal is split into parallel paths. Each path passes through a variable gain amplifier, or VGA. This component applies our windowing function, tapering the power at the edges to suppress side lobes. Next, the signal flows through a phase shifter, which applies the precise delay needed to steer the beam. Finally, a power amplifier boosts the signal before it radiates out into space. In reception mode, the process is essentially reversed. The weak incoming signal from space first hits a low-noise amplifier, or LNA, which boosts the signal without adding static. It then passes through the same phase shifters. But here is the magic. Instead of creating a delay to steer a beam out, the phase shifters now align the incoming waves from a specific direction so they arrive at the processor in perfect sync. This allows the system to listen intently to one specific patch of sky while ignoring noise from everywhere else. Now, a quick technical distinction. The method we just described, where phase shifting happens on the radio wave itself, is called analog beamforming. It is cost-effective and common in consumer terminals like Starlink. However, massive radar systems often use digital beamforming. Here, the phase shifting is done mathematically inside the processor, before the signal is even converted to analog. This offers ultimate flexibility, allowing the system to create multiple beams to track many targets simultaneously. Whether analog or digital, these systems perform the same feat, manipulating the fundamental physics of interference to connect us to the world at the speed of light.